Okay, ready for the second part? Good. So let's carry on with the materials for fuel cells, and let's talk about catalysts and electrodes. Now you saw actually the original cell we had, so that was very schematic, and you wouldn't use that actually for a fuel cell. When we want to design a fuel cell, we need first to develop some of the criteria that are important actually for it, and they're sort of listed here. What's the aim? We want to have actually large currents, and large currents means that I need to have a reaction that has a large exchange current density. That means rate constant actually in chemical reaction theory. And a large exchange current density depends usually on the kind of catalyst which I'm using on the surface. Typically, one uses noble metals, especially for the hydrogen and the oxygen reaction. They show, like platinum shows the best performance. Then I have actually some condition, just comes from the way actually I operate the fuel cell, is that the electrodes need to be gas permeable. I feed the gas, the hydrogen and the oxygen, and it needs to go through the electrodes to the catalyst particle, and that catalyst particle has to be in contact with the electrolyte. So I need to have a construction that I have an electrode material that's gas permeable and an electrode that allows actually this. Now when I look at platinum, then you see this is the number, 10 to the minus 7 weight% of the Earth's crust. This is really not very much. And this is actually exactly the reason that platinum is what's called a noble metal. In comparison to others like aluminum, iron, even copper, copper is 1 times 10 to the minus 2. This is 10 to the minus 7. So it's 5 orders of magnitude less abundant than even copper. Costs are pretty high, 40 euro per gram. That's about, I don't know, 300 RMB per gram, roughly. A lot of money, right? The way actually it's being made is also complicated. For 31 grams of platinum, you need 10 tons of ore, and you have a processing time of 5 months. So making the platinum as a raw material is expensive because it's not very abundant, and it's very complicated to make and takes a long time to make. So this is something one has to have in mind when you say, okay, let's take platinum. Yeah? You can take platinum in the lab, but when you want to have that, every car in China is equipped with a fuel cell, then you run into a problem with platinum. But we need something in addition to that. We need actually some other components. We need a so-called gas diffusion layer. I just said it has to be gas permeable. The catalyst layer, we have to see that we replace the platinum by actually some other catalysts. And we need, whenever we use the platinum, we need to make a large surface area for the total platinum. The ideal situation would be that every platinum I have sits on the surface of a particle, because then I can utilize it the best way. This is actually some very important aspect to follow, and that has entered actually this business. But then there's actually some sort of very subtle effects, I would say, is that taking a platinum and put this actually on some other metals introduces so-called substrate effects. That means that the bond lengths change, and that may have some positive effect on the electrocatalytic behavior, but may have actually also some opposing effect. So I have to find out what this combination means. So there are a number of things I need to understand before I can really make an ideal cell. But let's look at the, oops, this was not constructive. Sorry, you didn't notice it, but anyway, just a second. Oh, it's back, okay. Okay? Fine. Let's look at the way actually you can sort of put this then together. This part was what we looked at before. This is our membrane, and this is sort of our electrode. The electrode consists out of the catalyst layer and this gas diffusion layer. You see, you have this on both sides. And then outside of this, you need to have what then is called the interconnect, because you connect single cells to a stack, but you need to have actually a material where you have the gas distribution, the flow field with the gas distribution. That's very important because you need to transport the hydrogen here to your cell and the oxygen from the air here to your cell. So the way you construct this is also very important to see. Now let's look at some examples. For instance, these are typical gas diffusion layers. They are made actually of carbon fiber or carbon cloth or fiber paper, and this is a typical structure for cloth. It's actually simply like weaving it, right? You take actually some here single fibers, and then you weave this into the structure. It gives you some mechanical stability, but it allows you actually from the surface to penetrate this by gas. And this again here are the pores where you can have the gas penetrate, and at the same time you have actually electronic conductivity in the carbon to get the current out. And this would be sort of the gas transport from these flow channels, which I showed before, through the GDL, that's the gas diffusion layer, to the catalyst layer. And the catalyst layer also has to be porous because the gas goes through. You have the electrochemical reaction here, and then they go into the membrane. And you need then the electrons. Let's say from hydrogen oxidation, you release the electrons. These electrons have to go from the catalyst layer through the gas diffusion layer into the interconnect to make the electrical connection. So there is essentially are three flows actually. There's the hydrogen flow and the electron flow, the charge flow. And for the oxygen side, when you look at the cathode, is also that you have to transport the water away from the surface. So these are the criteria for these gas diffusion media, and this is essentially summarizing what I just said. Electronic conductivity, also heat conductivity, mechanical support, gas access, removal of gaseous products like water and others. Actually, when you use air, then you know air consists actually to about 70% of nitrogen. So you put actually the nitrogen in, and it has to go through and it has to go out again because it's not desired here. So in the end, the most important properties are the electronic conductivity and the gas permeability, and between these two typically you have to form actually some compromise that both are going actually with a sufficient rate. through it. This shows you actually some materials in micrographs. Here you have only carbon material. Then you have some PTFE. We talked about PTFE. So essentially PTFE itself is water repellent. And you put this in to get actually the water that's being produced by the reaction to get this actually out of the fuel cell, so that not the pores are blocked by water molecules. And this shows actually the chemical distribution of carbon, and here fluorine, that's by the PTFE, you can see the fluorine. So there are a number of pre-treatments of these media that are very important to do so that you get a full functioning of the fuel cell. Now, the catalyst support is typically that you use actually carbon particles, or let's say they are about 100 nanometers, 200 nanometers diameter, and then you put actually catalyst particle of a few nanometers onto the carbon particles. And the important aspect is that you provide the electronic contact between the catalyst particle and the GDL. At the same time, you get a fine distribution of the catalyst on the carbon itself and make a large surface area. And then there are sort of different criteria that are used actually in the fuel cell that you call this weight percentage. It's how much catalyst you have on the carbon particle. And for different reactions, this plays an important role, how high the weight percentage is, if you use hydrogen or you use other fuels. So that needs to be typically found out. And you have to make sure that there is not too much sort of particle growth or agglomeration or Ostwald ripening. Ostwald ripening is a process when you have a lot of very small particles, then actually the surface energy of a very small particle is very high, and sort of the surface atoms have the tendency to move around. And then they go actually not to a small particle, but they go rather to a large particle because the surface energy is lower. And everybody wants to go to lower energy, right? So when you stand for a while, then you say, oh, I'd rather sit down, actually, because it's more comfortable. That's a state of lower energy. And that's what the atoms also want to do. They want to go to lower energy. So then they tend to go all to the large particles because they have a lower surface energy. And the more they grow, the more atoms go there, and then they grow and the smaller ones disappear. And this is sort of the process of Ostwald ripening. And then the support, of course, is influenced. Here you have a table, you can look at this, you have all the papers, look at this in detail. You see the variation actually of these carbon materials. They have different surface areas, they have a different microporosity, they have different mesoporosity. All these factors play a role in operation of a fuel cell, but often in a different way. And so often what you do is you optimize, let's say with certain materials, certain operational conditions of the fuel cell. So this shows the way actually you can make these particles, the platinum particles, and there are also sort of certain ways. Here you see, actually this is like a bar here, this is 20 nanometers. So for this, no, actually this is a smaller bar here. This is for 2.2 nanometers is sort of here the distance. So you see that even these very small particles are essentially crystalline. So you get actually diffraction patterns, and you can actually see sort of the layers actually in the catalyst particle. So that can be identified And actually the way you do this is also depending on the process you're enduring. Now this shows actually then more in a realistic way, looking at the transmission electron micrograph, how a catalyst layer sort of looks. These are the carbon particles here, these gray areas. You know, carbon is a material that has a lower Z, so it's not that strong contrast in the transmission electron micrograph. So you see this actually as gray area, while the platinum particles you see as really dark spots. Here it's a little darker because you have more particles on top of each other, so they are stacked, and that makes it here a little darker. But in principle, the small particles are the platinum particles and the larger ones are the carbon. And this is like a typical situation of a technical catalyst for 2 nanometer platinum particle on a carbon support. And then you can vary actually the coverage, how much metal you put actually per square centimeter. That's shown here. That's sort of the variation, 8 milligram down to 0.2 milligram. Now I told you before, since platinum is such a expensive material, the ideal situation where that you have only surface atoms, but of course that's not possible, right? So you have to consider how much of surface versus bulk I have, and I use actually in the catalyst particle only the surface atoms. And this shows you actually the relationship between the surface area and the particle size. Now, as I told you before, there is sort of this effect when the particles are very small, you may have accelerated Ostwald ripening. That means that the particle coalesce and become bigger particles. So that means it's not stable. So I have to have a compromise between the stability of my catalyst particles and the exploitation of the surface area. And for that I need to know what that ratio is. And you see actually when you go from 20 nanometers down to about 2 or 1 nanometer, I see how steeply it increases the surface area. So a typical compromise between these two factors is to go to about anything between 2 and 4 nanometers. So this is the range that's typically used actually in a fuel cell. So you still have actually a fairly high surface area, but the stability is larger as if you would go actually here to these particles. And it's interesting to see that it's not a linear curve at all, but it's a very, very steep curve to the small particles. It's a 1 over R relationship. That's the reason that that looks like this. So now I have my catalyst particle. I know actually how to make it, and then the question is, how do I put this together then in the fuel cell? And there are essentially two ways of doing it. The one is that I put the catalyst layer actually onto the membrane, and then put the GDL layer here on top of it, make the contact between these. Or alternatively, I put my catalyst layer on the GDL. Why is it called GDE here and GDL here? Anyway. And then press this together actually with the membrane. This is the gas diffusion electrode, and this is then the gas diffusion layer. Oh, I see. Okay, the electrode then becomes, when you put the catalyst layer onto the GDL, it becomes a GDE. Okay, so both techniques are being used. So you can't really say that the one is much better than the other one. Depends a lot on what kind of materials you're using and how you want to make it. You see some of the techniques indicated here. You can have spraying That's a very common technique actually of spraying in ink. You make actually out of the catalyst that's supported on the carbon, you make an ink and you spray that ink actually onto the membrane and then put the electrodes on. Or you can also do some tape casting, printing, painting, but the spraying is actually the most common technique. And then you have actually to develop a technique that you can use also for industrial production, and people have done this. Again, here are the different steps. This is how to make that ink. This is just what I said. You can spray it, it's shown here. You can paint it. You can brush it, or you actually roll it on with the paint. That would be the ink application. And then you put actually all these layers together and have a so-called hot press, which typically is done at about 130 degrees. That is a temperature where the membrane actually, it's about the glass transition temperature of the membrane. And so the membrane becomes actually a little soft, and you make an intimate connection between these different layers and the membrane. Then this is actually what you get in the end. This shows a micrograph of this cross-section. This is the membrane, this is the catalyst layer, and this is the gas diffusion electrode, and this is the flow field providing the electrical contact and providing the gas diffusion. No, it's actually the other way around. This is the channel and this is the material here. Now I think you see, and this picture is actually schematic and shows you now actually how delicate in a way really the construction is. That you have some solid materials as well as these sort of flaky materials, because you need to bring the gas through this layer. This is here the gas diffusion layer, to the catalyst particle, here the carbon with the platinum on it, and you need to be in contact actually with the membrane, which for instance is a problem here. The gas comes in, here's the catalyst particle, but the way to the membrane is rather long, and I have to establish it, so I have to put some naphthalene here as well to get the ionic conductivity to the membrane. Otherwise, these particles are inactive. So the problem actually in my eyes, and the other picture shows that actually even more pronounced way, is still today there is no systematic approach to this, to making actually these structures in a fuel cell. It is complicated. You need to consider the pathway of electrons, the pathway of ions, and the pathway of the gases. That all has to function together, but it's actually done by trial and error. Now people are pretty good in doing this, but there is no systematic approach. And I believe, and I give this to you as a task, not to do and solve until Friday, but for your future, to develop rational techniques for doing this. Look at the microelectronics industry, what fine structures they can very accurately do and are very successful if you look at the making them more and more smaller. So when you look at the computing power of the mobile phones today, that's a result actually of this very rational approach of making nanostructures and microstructures. This is not a rational approach. It's just trial and error. And I think that's one of the drawbacks actually of the technique. And we have to come to the situation that we have a rational approach and have systematic structures being formed also for the fuel cell. Okay, so this concludes our consideration of the materials for the fuel cell, and the next step would be to look at hydrogen. How much time do we have actually for the hydrogen left? 20 minutes. Oh, that's actually not so bad. I thought we would be a little behind time. But let me actually show this to you, and the point is essentially we want to look at some aspects, how to make the hydrogen and how to store the hydrogen. So if we don't finish exactly today, it's no problem, then we will carry on Friday. Friday will be a little lighter in terms of the material anyway, so we don't worry about it. But looking at this possibility, or at the necessity actually, it's not only a possibility, it's a necessity of hydrogen production and storage, is intimately connected to the hydrogen fuel cell. If you have no hydrogen, you don't run a fuel cell. So, and if you don't know how to make the hydrogen and how to store the hydrogen, then you can't run a fuel cell. Now there are different ways of doing this, and this is sort of a very comprehensive picture actually of the different ways how you make the hydrogen and how you use the hydrogen. And let me explain that actually to you. The upper part is the making and sort of what are the supply possibilities for hydrogen. We talked about natural gas already. That's definitely a very important part. This is how most of the hydrogen today is being made. We will come actually to that distribution in a moment. But you can also make it from coal. Coal can be a source for hydrogen by making synthesis gas from coal, and then the synthesis gas contains hydrogen and carbon monoxide, and you separate the carbon monoxide and you have hydrogen. So let's say, even as we come back to this later, but let me say this already. China is a country that has a lot of coal reserves, as we have said, and if you want to change the energy situation and you want to use the resources you have from coal, then you can do this. You can change, actually you can have so-called clean coal technologies. And I think that's a very important area of research also by using this. But sort of the point to consider is you have to use technologies where you don't actually then throw the CO2 into the atmosphere, but you have to combine this with the so-called CCS, carbon capture and storage technology. Otherwise it doesn't make sense. Okay, again, there are a number of renewable energies. You can use solar thermal, biomass, solar PV, hydroelectric, and you can use actually some of this by using the electricity, and you can use nuclear electricity. But the problem, of course, is when you produce electricity here and then make hydrogen from it, and then from the hydrogen you make electricity again, this is a process that is very inefficient, and I show you actually one picture of this. When you produce electricity by renewables, you better use the electricity and you shut off the coal power plant. That's the best way actually of using this. But anyway, so these are in principle all the possibilities. That all goes to hydrogen, and then the hydrogen can be used in a fuel cell, but you can also use it actually for other transport. You can burn hydrogen in an internal combustion engine. There are different possibilities. You can then use the fuel cells also to supply buildings. In industry, you can use the hydrogen. It's actually, most of the hydrogen today is actually used in the petro industry, actually for processing crude oil to make gasoline from it. So you need a lot of hydrogen because the crude oil is much more carbon containing, and you need actually shorter chain lengths of hydrocarbons, and then you need to introduce a lot of hydrogen in order to break this down and make gasoline from it. So that's today actually the largest consumer of hydrogen in the industrial sector is essentially the petro industry. Now this shows exactly what I tried to indicate already. When you use actually hydrogen as a basic energy carrier, and there's sort of some talk about hydrogen economy, then you have to really look at what the losses are, and this is actually a description that sort of looks at these various factors that go into the losses. If I produce electricity regeneratively, let's say by solar or wind, then typically that electricity is, let's say, from large plants is AC, and then I convert this to DC, especially from wind energy. Solar would be DC to begin with. Okay, but anyway, I have electricity, and then I produce actually electrolysis, and for that I need direct current, and that efficiency of electrolysis may be about 60%, 70%. And that brings us actually down. When I have this here, I go down to here. Then I need to compress it for transport, and I need to transport it. Then I have actually a hydrogen tank, and then I bring down sort of the efficiency down to about 35%. I can also use in a fuel cell. But that efficiency is actually not much different. The average efficiency is just that the fuel cell is much cleaner than an internal combustion engine. So the overall situation is that I end up about here, actually at most here, 30% efficiency going from electricity through hydrogen back to electricity. And so that is actually really of concern, and I should use the electricity directly instead of making hydrogen out of it. Okay, but that's sort of the general description. Now when we go to the technical things, we have to distinguish for the hydrogen production what are actually the possibilities. There's reforming is an important process. What are future possibilities? High temperature electrolysis is, especially today, discussed. It has the advantage of having a higher efficiency than low temperature electrolysis. You can also make it photochemically or photoelectrochemically. These are actually some of the things. There's some question about efficiency as well, but these are interesting techniques. And then I have to look also at the question of hydrogen storage, and there are different means. I just compress it. I go to a liquid. That means I have a liquefaction. I store it in hydrides or in other chemicals, and there are sort of some new fancy molecules like MOFs, metallic organic frameworks, and nanocarbon that may be able to store actually a lot of hydrogen. So let's go through some of them. We will not discuss everything in great detail, but some of them. Actually this is some literature. You have the printout. You just look at this if you want to see more about it. Okay, we have looked at this graph which sort of contrasts the supply side as well as the consumption side or the demand side. Let's look at the pros and cons of hydrogen again, of hydrogen technology. So one of the advantages, and it's really interesting actually to see, is that hydrogen is the most abundant element on Earth. Hydrogen appears everywhere. So that is really interesting. But at the same time, we know that hydrogen is not a primary energy carrier. So that means I always have to have a process that makes the hydrogen out of other sort of fuels or components. And it can be obtained from different resources, but I need then also to worry about how to store it, either by compression or liquefaction, and that may be actually complicated and expensive. Definitely, using hydrogen is environmentally benign, because the only reaction product of hydrogen is actually water. So that's an ideal situation. But we know that we have to make it from some other carrier, and so we have to consider that there are other processes. Now, the disadvantage of hydrogen itself is it has a low energy density. Even if you have liquid hydrogen, and liquid hydrogen requires a lot of energy actually to make. So that's definitely a downside. But even liquid hydrogen contains only 25% of the energy of 1 liter of gasoline. So if I go then even to, let's say, not liquid nitrogen, I think there's a table later, but to compressed hydrogen, which is easier to make, still needs some energy, but easier, then the energy content goes further down. So it's actually less than 10% of gasoline. Handling is not complicated, there's a large experience. However, when I have leakage, I may have a problem, because the ignition range of hydrogen with oxygen is very wide, and wide range of compositions, and it needs only a low ignition energy to get it sort of ignited. So that's definitely a problem. So this shows, and that, what, 20? Okay, good. This shows actually hydrogen production today. I told you actually. Natural gas is by far the largest source of hydrogen today. Close to 50% of all hydrogen is based on natural gas. You can also make it from mineral oil by cracking the mineral oil, and then have actually a reforming process similar to what you do actually with the natural gas. That's 30%, and that's mainly done actually in the refineries, where you need a lot of hydrogen to change the crude oil to gasoline. So they make actually just also some hydrogen from the same raw material. You can also use charcoal, and you can use electrolysis, but you see electrolysis is not very common. Just 4% of all the hydrogen is made by electrolysis. And the reason is simple. You need electricity, you need electric energy, and that's usually not cheap. It's expensive. So most of that is being done, let's say, close to hydropower stations, because in hydropower the electricity is rather cheap, and then they also use that actually for making hydrogen out of it. So why do you need actually all hydrogen? There are two major applications. One I mentioned already, it's the refining actually of crude oil, very important. But the other one is actually very important for agriculture, is to make ammonia. And ammonia is the basis actually for fertilizers in agriculture. And a lot of hydrogen is essentially needed there. And you probably all have heard about a very old process, that's Haber-Bosch process for making actually ammonia, which has really revolutionized actually the agriculture situation by being able to make fertilizers in a rather affordable way. and make artificial fertilizers and not being dependent on manure from animals and all this. So let's look at some other possibilities when we look actually at renewable sources as well. Biomass can be a source of hydrogen. You can have a biomass gasification process. What you typically do is actually a production of synthesis gas. That means the mixture of CO and hydrogen. And then you can use that mixture and make hydrogen from it. But you can also use the synthesis gas to make actually some other fuels from it. You can make, for instance, ethanol from it, or methanol, or also hydrocarbons. So that's a possibility for biomass. But you can also biomass when it's ready, and we will see this for ethanol. You can actually ferment this and make ethanol from it. Wind energy is a possibility, but I said already it would be better actually to replace the electricity of coal power plants by the electricity of wind as far as you can. But there may be peak power or whatever, and then you can use an electrolysis process. Import, now of course you can import everything, so that's not a real source of, natural source of hydrogen. But this may be actually an interesting point here. I mentioned this already. Gasification of coal may be actually even an economical option, but you need, as I said, you need to have CCS combined with this so that you actually have no emissions of CO2. So that's very important. And this would be natural gas, which I mentioned already. So this would be actually sort of the way actually of doing the major form actually of hydrogen production, that is sort of by reforming. There's steam reforming, there's partial oxidation, there's autothermal reforming, gasification, and anaerobic digestion. So we have a lot of possibilities. And we will look essentially at these three, because these are the ones that are mostly used in industry and are very important. Again, there is some background reading which you can do. You have the information. You can read about this. Now, let's look at the most common process for reforming, and that is the steam reforming. And the steam reforming has a clear advantage, which you will see by comparing the techniques, and that is that it has actually fairly high efficiency in making hydrogen. But as you can see also, there are various steps that are involved. So first you have to make steam. You preheat this, you have a catalytic fuel reformer. You have a water gas shift reactor, then you need some CO cleanup, and then you can give it actually into a fuel cell. So there are different steps actually involved in doing this, and then for the fuel cell you would actually then downstream have also catalytic afterburner, so to remove actually hydrogen that's still left there and some other gases. Now let's look at the reactions that go on, the chemical reactions, and they are sort of determined by the reactions themselves. This is like methane plus water gives CO and hydrogen. I mentioned this before. This is like synthesis gas. Now, what happens at the same time is another reaction that you always have to take into account, and this is this reaction. This is so-called water gas shift reaction. And this is typically in equilibrium, and since it has a negative sign, that means it's an exothermic reaction, while this is endothermic. So you have to deliver heat to drive this reaction. The question of the products depends very much on the temperature. So when you go to a high temperature, then essentially you get the left side, because it's exothermic, you drive it actually to this side. When you go to low temperature, you drive it to this side. Now, having actually a typical reactor temperature, let's say for methane, you use something like 800 degrees is the typical reforming temperature. And then you can see, here you see this is the sort of different concentrations, and you see at about 750 you start having all the methane react. So you go to 750 to 800 because then you have complete reaction of the methane. And then you look actually at these concentrations, and at 800 you see you have a considerable amount of CO here. It's above 10%, maybe 14%. Then you have water, and here's the hydrogen, and this is the sort of the CO2. So depending on the application, when you go, let's say, want to feed this into a fuel cell, then the first thing you need to do is remove actually all this carbon monoxide, because carbon monoxide is actually a poison for the catalyst, and having 12% is not very good. So what you need to do is reduce this to a few ppm, enormous task. And what you need to do is have actually shift converter, and shift converter are reactors that operate at different temperatures, so that you are able to operate them at lower temperatures to shift this actually to hydrogen, so that you get more hydrogen and less CO, so that you drive the reaction from left to right. That happens at lower temperatures. But at lower temperatures, typically the reactivity is not high enough, so you need actually a catalytic process. And that's sort of shown here, actually, that for the different stages, you need different kind of catalyst. Nickel is typically a catalyst for the reforming, but for the gas shift reaction at high temperatures, you have like a mixture of iron oxide and chromium oxide, and at lower temperatures, you need actually a copper catalyst on a zinc oxide support, which is actually a reforming reactor also for methanol. So it shows in the end it works, everything works, but these are various stages you have to go through, and it's a bit complicated actually what needs to be done. But the industry is fairly well established, one has to say. Now, when you take actually methanol and try to make hydrogen from it, because there was some concept of saying it's so difficult to store the hydrogen when you have a car, and I want to drive with a fuel cell, maybe I take methanol and then reform methanol in the car to make hydrogen from it. So people have considered the situation of methanol steam reforming, it can actually sort of substitute then fossil hydrocarbons, and the reforming is actually much simpler than that of let's say methane and other hydrocarbons, because you can do the reforming actually at a temperature of about 300 degrees or even below that. So that's a big advantage. You still need actually the water-gas shift reaction, but you need only the lower temperature stage, because the operating temperature is much lower already. So that's a big advantage. So in total, when you look at methanol steam reforming, these are sort of the parameters for it. You can operate it at lower temperatures. You need only one shift reactor compared to methane, and that makes actually that process simpler, less expensive, but you have to know where does my methanol come from. So that would be actually a concept then, having a fuel cell that runs on methanol as the as the fuel. Let's say this would be like a fuel cartridge. So you can apply this actually even to smaller systems. And then you do the reforming, where you integrate actually a shift converter and actually a purification of the gas, and then have a fuel cell stack and then get your water out. So there have been actually a number of attempts to make a fuel cell system that operates on methanol, but not direct methanol, but actually reformed methanol. And this is the concept for doing it. Okay, I think this is sort of more or less what we want to discuss today. And then we will actually look at this hydrogen production and storage then on Friday initially, and then carry on with the other topics. So thank you very much for your attention today, and I wish you a good evening. Thank you.